Hello, in this lecture we start studying some details of statistical learning. In particular, we will study what models are good for, and also we will start to see how model accuracy can be assessed from the data. So this is an important lecture. Many important notions will be introduced, and let's start with a question. What is statistical learning? We start with an example. So we have this data where we have sales, and this is the result of an ad campaign. So money has been spent in advertisements, and these advertisements were advertisements on TV, on radio, and on newspapers. So we have three independent variables, and the final goal is to increase sales. So a first thing we can do is to look at the data, and so we just display the scatter plots of the money spent on TV against sales, money spent on radio against sales, and money spent on newspapers against sales. And the data are just the red circles, and you can see also blue lines, and these blue lines were obtained by linear regression. So our objective is predicting sales given our information on the independent variables TV, radio, and newspaper money. And okay, one could think of making predictions just using one variable at a time, and this could be done by means of the regression line. But of course, there is the possibility that putting together all the information, if we exploit jointly the information on TV, radio, and newspaper expenditure, we can do better. So the idea is, can we predict sales as a function of TV, radio, and newspaper money, the money that was spent on ads going on TV, radio, and newspaper. So this is a good example. And now the question is, what kind of function should we look for? But before, let's introduce a bit of notation. So hereafter, we will have a response or target variables. In the example, sales is the response or target variable that we would like to predict, and we will denote this variable as y. And on the other hand, TV, but also radio and newspaper, is what we call an input or a feature or a predictor. And the symbol that will be used will be x1, x2, and so on. So each of the predictors will be denoted by x sub I. And it is useful to collect all the predictors within a unique vector. So we can define a vector x, which in this example will be made by x1, x2, and x3. x1 is the money spent on TV, x2 is the money spent on radio advertisements, and x3 is the money spent on newspaper ads. Now, we can formulate the model we are looking for in this way. So the idea is that the target variable should be equal to some function of x, and beware that this is a function of three variables now, because x is a vector, plus some error. So because we cannot think of being able to predict perfectly y, so we should account for measurement errors and all kind of discrepancies between our model and reality. And what is f of x good for? Why are we looking for f of x? Well, the answer is quite simple. If I have a good f, I can make predictions, and predictions that should be made at new points of the feature vector x. So, for instance, if I have a good function that makes good predictions, I could consider different compositions of the expenditure. So I could decide that I want to spend more money on TV ads, and I would like to know if I change my composition of the money that I spent, if I change it, if I'm going to improve the sales. And if the function f is good, I will be able to predict if I'm going to improve or I'm going to worsen. And not only this, I could also understand which components of the feature vector x are most important in order to explain y, and also which are irrelevant. So it might be that some of these inputs, as a matter of fact, are useless because they do not affect y, or at least they do not affect the predictions of y. And this is another example. I could study the income of people, and the idea is that the income of some guy should depend on seniority and also years of education. And we can think that this is going to have some impact, a big impact actually. But for instance, marital status, a bachelor or married, may be not so important. This is our prejudice. And also, depending on the complexity of f, we may be able to understand also how each of the components of x is going to affect y. So the idea is being able to make good predictions, but also to understand some mechanisms that are behind our system at study. And okay, but could we say something about the ideal predictor f of x? So is theory going to tell us something about the best choice I could make? To address this issue, let's consider a very simple problem where we have just two variables. So we have x and y. This means that we have a target variable. This is quite common that we consider one target variable at a time. But then we have also one predictor variable, just one. So this is just a case of we have a scalar feature. So this is the most simple problem we can think of in a regression context. And here I am representing some data by means of a scatter plot. So I have a scatter plot of pairs x and y, and this can be seen as a historical data. So they just give a picture of how y depends on x in a variety of previous examples. And now I pose the question. If I select a value for x, for instance, x equal to 4, what's the best prediction for the target variable y? Something that is apparent is that if I fix x equal to 4, I can see that there are many possible values for y, so there is not a unique value. In this particular example may seem that it happens if I move to the extremes. In these cases, it seems, but this could be explained by the fact that we have only few data. But here at the center, we have many possible values for y. And now, if I use statistics to decide, I can see that a good value for the prediction is just the expected value of y given x. What does it mean, expected value of y given x? It means that I'm going to take all the values of y when x is equal to 4. So I'm conditioning this distribution on x equal to 4, because as you see, this is the scatter plot of a bivariate joint distribution. But if I fix the value of x equal to 4, then the conditional distribution of y given x is a univariate probability distribution. And I take this distribution, and among all possible values of the distribution, I just select the expectation. So this is the expected value of y given x equal to 4. And this value has some nice property, as we will see, so it is justified to choose this, but at this point I would like to stress that now I can move x, the value of x. I've taken x equal to 4, but I could take x equal to 4.5 or x equal 5, and I can replicate the same rationale. So also if I take x equal to 5, then I just draw a vertical line. I select the values of y in correspondence of x equal to 5, and again I'm going to take the conditional expectation, the average value of y given x equal to 5. Here I'm assuming that the number of collected data are so many that there is no difference between the sample mean and the theoretical mean. In principle, I would prefer to use the theoretical mean, so the real expectation of the conditional distribution. And now I just have another optimal prediction, and I can see that as I move x along the x-axis, I get optimal predictions defined by the conditional expectation of y given x equal capital X equal small x, and in this way I can draw this red line. This red line is the curve of the conditional expectation as a function of x, and its name is regression function. So we have good reasons to believe that this is a good choice for our prediction. So the idea is that I should take the conditional expectation of the target variable given the inputs, given the feature vector. Okay. It seems very simple. In some sense, it seems that we have solved the problem. So why should we study statistical learning theory, spend lots of hours if the solution is so simple? Well, as a matter of fact, it is not that simple, because we don't know the theoretical joint distribution of x and y. If we knew the expression for this distribution, then we could just take the conditional expectation of y given the vector x. And okay, so as a matter of fact, there is a lot of work still to be done, even if we have this guideline as for what concerns the optimal prediction. And first step now is to recognize that what I've said about the regression function holds also when x is not a scalar as it was here, but x in general is a vector. In that case, the regression function will be a function of the entries of this vector, so a function of x1, x2, and 3, and it is just the conditional expectation of the target variable given all the features. Now, of course, we don't have a regression curve, but for instance, if we had just two features, so x1 and x2, we would have a function of two variables, so we would have a regression surface. In this case, we have a function of three variables, so this is a kind of regression volume, if you like. Okay, and this is the ideal of the optimal predictor, and you could ask why is it the ideal one? Well, it is the ideal one because the conditional expectation is the function that minimizes the expected squared error over all possible functions at all points x equal small x. So let's go here and have a look at the error. So this is the difference between the target variable and a prediction g of x. So g is a predictor. Okay, we take the square of the error. Okay, so we would like that the square of the error be small, which is very, very reasonable as a requirement. And of course, we know the value of the feature vector, which is equal to small x. So this is a random quantity, unfortunately. We know there is randomness, recall the error term epsilon. So this is a random term, and of course we are not interested in what happens for some x different from the one that we have observed in the real data. So the question is, what is the squared error when capital X is equal to some specified feature vector? So this is a random quantity. This is conditional on the knowledge that I have on the feature vector. And of course, here we have a distribution, and the point is that I would like that this error is small on the average, and so I take the expectation. So my desire is that, okay, I cannot have a zero error, that would be too much to ask for, but I'm content if the expected value of the squared error is as small as possible. Now we have this statistical result that tells us that among all possible functions g of x, this function f of x given by the conditional expectation minimizes this quantity. So you cannot do better if your objective is minimizing the conditional squared error. But this is a very reasonable target, this minimization. So in some sense we can actually say that the conditional expectation is the best possible choice. Here, epsilon, that is defined as the difference between y and the regression function, will be called hereafter the irreducible error. So the idea is that I'm making the best possible prediction, but still I will not be able to obtain the actual value of y. Well, that would be magic if I could. And therefore there is still an error, but this is the small, in some sense, is the smallest error or the irreducible error that I cannot avoid. And this is hereafter the irreducible error. And for any estimate f hat of x, so of course I would like to use the regression function, but as we have already discussed, I can compute the exact f only if I know the true distribution, and in general I will not know the true distribution. So I will be forced to use some f hat that hopefully is close to f, but it's not perfectly equal to f. For any estimate of this kind, there holds this result that says that the squared error that I commit using f hat, as usual, I consider the error conditional on a specific value of the feature vector, can be decomposed in two terms. So I have the irreducible error, so this squared error is equal to the variance of the irreducible error, and okay, there's nothing to do with the irreducible error. Even if I was able to estimate the true f, the true regression function, the irreducible errors would still be there, okay, plus the square of the difference between f and f hat. So this is the error that I commit in approximating the true regression function. So I have some error that I cannot do anything. This is something I can work on. So I could try to have an f hat as close as possible to f, because of course the best possible result is obtained when f hat is equal to f, in which case I just have the variance of the reducible error as equal to the squared value of the prediction error on the target variable. Now, but this is theory, so on, and we would like to estimate f in the real world. So, how to estimate f? This is the question at this point. And we are somehow in trouble. We are going back now. Let's go back to the this example. So this seems quite easy because when I have x equal to 4, I have a lot of values. Okay, I have a lot of circles, so I could use these circles to have an idea of the distribution of y given x, and once I have an idea of this distribution, it's easy to go for also the conditional expectation, to have an estimate of the conditional expectation. I could even obtain an estimate of the conditional expectation directly from the data. There are so many that this does not seem a very hard problem. But in practice, it will happen that I'm not so lucky. And this could be a more realistic situation. So I have these data that are the black circles. Okay, this is x equal to 4. And I would like to predict y. And how can I do? You can start observing that if I take x equal to 4, if I fix x equal to 4, I do not have data. So there is no circle that corresponds perfectly to x equal to 4. Therefore, I cannot compute the conditional expectation of y given x by means of some sample average, because I have no data to average. Okay, so in order to have an idea of this conditional expectation, I have to relax the definition, and instead of taking the conditional expectation when x is exactly equal to small x, I will consider just a band. So I define a band around x equal to 4. In this way, if I define this small band, I can get some data, okay, and I'm going to averaging these data. So now my f hat, my predictor, will be the average of y, of the target variable, when x belongs to some neighborhood of x. Here the neighborhood is defined by means of the distance measured as difference between the x variables. So I take all the circles that are close enough to 4, whose x-coordinate is close enough to 4. Of course, I have to define this neighborhood in some way, and this is the way this has been done here. So I just take these values, these black values, I take the average, and so I have the prediction. I can repeat this procedure for all possible values of x. So if I have x equal to 5, I will have another band. I will take all the data that belong to this band, and then I will be able to compute the average of the target variable. If I do this, I get this kind of curve. Okay, and as you see, this could be, at least in this case, a rather reasonable approximation of the conditional expectation I'm looking for. Okay, but recall that this is a very simple problem, because in this problem we just have one feature variable and one target. So this is really a simple one. And so there is a warning that this near neighbor averaging, which is very intuitive, very simple, can be pretty good for small p. What is p? P is the number of predictors. So is the number of input variables, and rule of thumb could be that p less than or equal to 4, and also this method can be pretty good if you have a capital N. What is capital N? Is the number of data, the number of training data, we could say, if the number of data is quite large. So if I have a large number of data, I'm using a few predictors, I could try to approximate the regression function by means of some neighbor averaging. There are also other ways to get some approximation of the regression function, and this method can also give you approximation that are smoother than this one. You can see here then this is not completely smooth, but you have change of slopes change of slope at some times, and so on. And these methods are called kernel and spline smoothing, and we will discuss them later in the course. It has to be said that nearest neighbor methods can be bad when P is large. Why? The reason is due to what's called the curse of dimensionality, la maledizione della dimensionalità. We will try to explain by a plot, but the point is that if you have to make an averaging, you need data. You need data, and so your neighborhood should be large enough to collect then a certain number of data so that your average can be made and is reliable. But unfortunately, in higher dimensions, so when the number of inputs is large, in order to collect a sufficient number of neighbors, you have to take them far away from the point X you are interested in. Okay, and so you have a problem, because if they are far away, they are not representative of the regression function for that particular X. This is explained here. So we need a reasonable fraction of the n observed data to make a good average. Say you need 10% of this data, but a 10% neighborhood in high dimension is no longer a local one. And therefore, the approximation of the regression function worsens significantly. Let's have a look here. So here you have x1 and x2. You can imagine that these are two feature variables, and if I consider just x1, the notion of neighborhood brings you a band. So the idea is that a neighbor is a point which is close to the red one for what concerns the sole coordinate x1, and therefore all the points in this band are neighbors to the red point. And the idea is that the band has been chosen in such a way that I have about 10%. I have 10% of the data in this neighborhood, and you can see that this neighborhood is reasonably local. So I have 10% of the data, which guarantees that my averaging will be a good average, but I have not taken points that are far away from the red one. But if I consider two features, so I have x1 and x2, okay, now the notion of neighborhood is given by a radial distance. So the idea is that a point is a neighbor of the red one if its distance measured in a Euclidean way is small enough. This produces a boundary for the neighborhood, which is circular. Again, I take a neighborhood in such a way that inside it have 10% of the data, and I can see that this is the neighborhood, but in some way it is less local than the one-dimensional one. As you see, this has become quite a large neighborhood. If I repeated this procedure in 3 dimensions, I would have a sphere, a ball. I would have a ball, and again, you would see that in order to capture 10% of the data, the radius of the ball should be quite large. This is something that you can see here. So we have fraction of the volume. For simplicity, I am assuming that the data are uniformly distributed in a hypercube, for instance. Here they are uniformly distributed in a square, but imagine that they are uniformly distributed in a hypercube, and I define neighborhood in such a way that the neighbors the neighborhood captures 10% of the data. Now, what does it happen? That as I move from one dimension it was x1, 2 dimension was x1 and x2, 3 dimension is the case of the ball, I will find out that the radius that I need to take, so I have to take a hypersphere to describe the boundary of the neighborhood, the radius of the hypersphere is going to increase very much. Okay, as long as the fraction of the volume, I want it to be 10%, but okay, this is just to have enough data when I take the average. Okay, this is called course of dimensionality, and it explains that there is no easy way to obtain the regression function in high dimension. So if you have p that is small, you have a large number of data, then your life is easy. Okay, you can even go for nearest neighbor technique, but in more complex cases, this will not be the solution. Therefore, we are looking for other kinds of models, and in particular, we can use one of the typical models that are used in statistics and in all other fields, that is the linear model. So this is an important example of a parametric model. So the idea that our predictor is a linear function of the entries of x. The expression will be beta 0 plus beta 1 x1 plus beta 2 x2 plus beta p xp. Here we are using the typical notation of statistics, where the parameters are called beta. In my model identification course in the bachelor degree, I use theta, okay, but here we are following Hasti and Tibshirani, and therefore we will adopt the statistical notation. So we call beta 0, beta 1, beta 2 the unknown parameters. These p plus 1 parameters completely specify the model, and you can see that we have p plus 1 because there is also beta 0. And these parameters can be estimated by fitting the model to the training data, that is by solving a least squares problem, a linear least squares problem for which an explicit formula is available. Okay, this is a model. The advantage is that it is very simple, but of course it is almost never correct, because you must be very lucky to find a real-world problem where the regression function is exactly a linear function of the features. But nevertheless, a linear model has many advantages and can be used as a good and interpretable approximation to the unknown true function. So even if wrong, it could be still very, very useful. And we can see the linear model at work here. So we have our data. We are interested again in finding a prediction in correspondence of x equal to 4. We fit a linear model. In this case, since we have just one feature, so p equal to 1, the model is just a line, the linear model. We have two parameters, beta hat 0, beta hat 1. The blue line is the fitted model, and we find our prediction. Is this a good model? Well, I'm not that sure, because I can see that the data show a shape that is a bit more complex than a linear one. So I could also go for a quadratic model that we call f hat q. And here is the model. As you can see, this model has 3 parameters here, because we have the known term, the linear coefficient, and the coefficient for the quadratic term. And it seems that this fits the data slightly better, so this curve is a bit more convincing. It could be that this is closer to the true regression function that possibly is neither linear nor quadratic, but the quadratic function could be a better approximation. Okay, all of this can be replicated also in more than one dimension, of course, when, for instance, p is equal to 2. Okay, if p is equal to 2, we have already said that the regression function is actually a regression surface, because f hat is f hat of x1 and x2. So our challenge is finding a good surface that closely approximates the true regression function. Here we have a simulated data set. The idea is that the income of individuals depends on years of education and seniority, and therefore the idea is that the data were simulated assuming some dependence that is given by the surface, and the surface is the true regression function, the true regression surface, and then random error was added in such a way that the data are not perfectly on the surface. Okay, so this is the way the data were simulated. So some f was assumed, and this is the in our simulated problem will play the role of the true regression function. Random error epsilon was added, and this generated the data. The blue surface is our regression function. Now the challenge now is to approximate this surface, and if we go for a linear regression model, in this case the linear regression model will give you a plane, because a linear function of x1 and x2 is just a plane. So f hat L stands for linear, now will be b hat 0 plus b hat 1 times education plus b hat 2 times seniority, and as you can see, that's not bad. So it's not the true regression, the regression surface, but it could be a reasonable approximation. But we can do better. So we could fit a more flexible regression model. For instance, this is the result that would be obtained by using a technique that is called thin plate spline. Splines will be studied later in the course. The characteristic of this modeling technique is that they provide a flexible way to approximate functions, in this case a flexible way to approximate a surface. Another nice feature of this method is that you can control the roughness of the fit. So there is a parameter that allows you to have a surface which is more or less rigid, to say. And for instance, I can make the function more flexible, and as a matter of fact, here it is so flexible that the training data are perfectly approximated. So we have no error on the training data, and this to the non-expert user could seem very nice. So I'm committing zero error. What's best than zero error? But unfortunately, this is a zero error on the training, but we would like zero error on our future predictions. And if you get zero error on the training data, on the past data, there is no guarantee that you will perform well on the future data. So when this happens, usually you are in presence of what is known as overfitting. So you are fitting the data too much.